We're now going to have a second look at the model architecture. I know we looked at this before, but I want to take another look just to point out some of the details of this model architecture. So first of all, we have an input image. We knew that from before. It's structured in a way such that it's 84 by 84 pixels, and then it's split up into 4 dimensions as well. So these all make it to the input of the network. And the first thing that happens inside the network is basically 3 convolutional filters are applied. Now, the first one has 32 filters and they're all 8 by 8 in size and have a stride 4. So the stride is basically how quick the filter or how many steps the filter takes as it sweeps over the input image. So these filters can identify features in the image. That's sort of how convolutional filters work. And the stride, if it's big, takes bigger steps as it looks with this sort of magnifying glass, if you will, at parts of the image. Next network is another 64 filtered convolutional network with a 4 by 4 size and a stride of 2. So half the stride size and then twice as many filters this time. Then there's another convolutional filters or convolutional filter layer, this time with 64 filters and 3 by 3 in size and a stride of 1. So they only take single steps. The last parts of this network are fully connected layers. So firstly, a fully connected layer with 512 rectifier units, and then a fully connected output layer with a single output for each valid action. So one thing that you can observe here is that the input is an image and the output is basically the potential actions that we have at our disposal. And so the output then, what the values actually correspond to are the Q values of the individual actions. And with a network structured in this way, given the input state, you can then evaluate the Q values for all actions with a single pass through the network. So you would supply an image here and you would get the output for every action here, which is a big benefit of a network like this, because basically you only need to send your data through the network once to evaluate all actions. Another sort of intuitive way of structuring one of these networks would be to supply both the state here, but also the action of interest, because if we think about what the Q function does, which we're really trying to approximate here, it takes a state and an action and then produces a Q value. So you could make a scalar valued function approximator that also takes into the action and then gives the output. That would be sort of the natural or first interpretation of what to do. The problem with doing that, however, is then you would need to basically do a forward pass for each action, right? So you would only get the corresponding Q value for one action. And structuring it in this way allows for all the Q values to be evaluated at once, which is a good thing from a data efficiency point of view. Next thing we're going to look at is some of the training details that were used basically during the training procedure for this network. So as we said before, there was a separate network for each game. However, the architecture of this network, like we just looked at, and also the learning algorithm and hyperparameter settings were the same for every game that was evaluated. So the results that are indicated by this paper really convey that this is one framework that can be applied to a number of tasks and performs well for all of them. So that's quite something. And the parameter values were informally selected, just as a side note, due to a data constraint or computational requirement constraints. Basically, evaluating these in a structured way will require lots of computation, and for that reason, they were informally selected. A tiny side note on the training details is that the positive rewards were also clipped at 1 and negative rewards at -1 in order to make the same learning procedure or same learning rate across multiple games feasible. If that varies a lot, the learning rate will have to change, and sort of the restriction you're doing in that case is that your model is unable to separate between very large rewards and smaller ones. So there's a loss in granularity there, but that's one of the restrictions that were made during the evaluation procedure. If we look at all the prior knowledge that was used, we can see that in this table. And this is basically everything, in every way that we're helping the model. So the model was supplied a life count, which helps keep track of when the procedure is over or when the game is over. So when the life count goes to 0, that basically means game over. It was given the number of actions, however, not their correspondence. So it knows basically if you can go up, left, right, or down, let's say, if those are the actions. It gives you basically the number of outputs. So the model knows how many outputs it can expect, but it doesn't know what they're linking to in the actual game. It gives the network the game-specific score as a way of trying to maximize that. And then it gives it the input data in terms of visual images. So very limited in the number of or in the amount of information that we're given the model beforehand. So there's no internal representation, for example, as could be expected from the model that's going to perform on tasks like this, and that's a big benefit. Also looking at some of the specific features of this procedure that was used, the algorithm is RMS prop. We won't go into details of that algorithm here, but there will be a separate video if you're interested in digging into the details of that. The behavioral policy that was followed during the training was an epsilon greedy policy. So this was, an off policy evaluation procedure, which is required basically when you're using the batch learning or the memory feature that was used in the training procedure. So because of that, you're sampling the training events basically from a distribution that's not the same as you're acting based on. So per definition, let's say it's going to be off policy. And the one that was used as a behavioral policy then, which is what we follow when we train the network, is an epsilon greedy one. We can see above this table here a graph of basically the epsilon value. So the epsilon value was set to vary across the number of iterations. So the frame that was observed is plotted on the x-axis here, and the epsilon value is plotted on the y-axis. We can see that on the first frame, we used an epsilon, or it was used an epsilon value of 1, and then it was decayed all the way up until the millionth frame. And after that, it was left at 0.1. So when it's 1, that basically means we pick an action at random all the time. And when it's 0.1, it means we take a random action 10% of the time. This is to limit the effect or the potential effect of overfitting or getting stuck in sort of the same, lower subspaces or small sub-regions of actions that we can potentially take. In total, 50 million training frames were used in the training procedure, which corresponds to about 38 days of training or gameplay. The replay memory that was used was 1 million frames, and those were the most recent frames. So you would keep the 1 million recent frames and then draw samples from that in order to train the model. Also, a frame skipping procedure was used, which means that you're taking one action and then you're skipping the next consecutive frames, specifically the next 4 frames in the case of this model. The reason why you do that is because you don't necessarily need to make an action or a new action at every frame because it's quite high frequency. And evaluating every frame for an action is quite computationally demanding. Whereas if you skip the frames, you can play a lot more with less computational requirements. So you can basically increase the amount of training that you get for a very similar behavior. The actions that were used as a sort of consequence of this, or the actions that were used in the skipped frames are the same as the action picked just before. So you basically take the action and then add it 4 times. So that's the procedure that was used, and it's a small, it is a trade-off, but the benefit of it is you can run your model on basically 4 times as much data. Looking at some of the details for the evaluation procedure as well, the networks were evaluated 30 times per game and then average for their score, up to 5 minutes of gameplay each time. And they were given different initial conditions, and they followed an epsilon greedy policy with epsilon 0.05 to minimize the possibility of overfitting during evaluation. So this is the evaluation procedure and not the training procedure, just to be clear about that. The random agents chose random actions at 10 hertz, repeating its last action on intervening frames. So the 10 hertz were picked because 10 hertz is roughly how fast a human can press a button. So you can recall from the performance graph that we had that basically a random agent was used as a reference because you're going to accumulate some score even if you perform fully randomly. So that's sort of the baseline for what you could expect. And then, as the final benchmark, a human professional tester played the games, and it used the same 60 hertz muted emulator as the agent did. So the agent doesn't have information about, sound basically when it evaluates this. So it was muted for the professional tester so that there wouldn't be basically a bias, or that the human tester wouldn't have any more information than the algorithm did. The human was not allowed to pause, save, or reload the games to basically even the playing field. And the human reward was averaged from around 20 episodes of each game, up to 5 minutes there as well, following around 2 hours of practice playing each game. Okay. And then the algorithm. So the environment is generally stochastic, and the score is path dependent, and that needs to be taken into account in the algorithm which is used for training. It's a partially observed task because we're only observing the screen and not the internal state. So when the agent is faced with basically the Atari game, it sees the screen, but it doesn't see the underlying structure. One example where this might be a problem is, let's say, the Pong game, which is where you're playing ping pong and you need to basically cover the ball from crossing your line. And if you only have one frame to base that on, it's going to be very hard to determine, or impossible to determine, the trajectory of your of the ping pong ball. You can see where it is, but you don't see where it's going, which is a major problem. So this is an example of a path-dependent problem, and the rewards of these path-dependent problems may be delayed by thousands of steps as well. So there may be very delayed rewards in some of these games, and that needs to be taken into account by the model. So as a result, sequences of actions and observations are used as algorithm inputs, and then the algorithm learns gaming strategies by approximating the Q function and of these actions, and it does so by limiting the loss function, which is displayed here. We won't go into the details of the derivation of this loss function, but nevertheless, we have a loss function where we have a basically target that we're trying to approximate and minimize the error from. And this can be done with gradient descent. So if we differentiate the expression for the loss function and then try to minimize that by finding where the derivative is 0, then that's a way to solve that problem. And one thing to note is that the gradient here can often be minimized or optimized by stochastic gradient descent rather than some more formal evaluation. So because we have an expectation here, if we can evaluate or approximate whatever is inside here, if we just do samples of that, random samples according to the same distribution, then we will get a value for this loss function. So it can be empirically estimated in a good way. One thing to note as well is that this algorithm is model free and off policy. So off policy we discussed before. It's off policy as per construction because we're using the replay memory, and that's not going to be on policy because we're sampling from a different distribution. So there it's really a no-brainer, or there's nothing to do about that. The fact that it's model free, we can see that because we don't have an internal state representation of the model. It's as we said, a partially observed problem, because we only see the screen and we don't have an internal model of what is actually happening. Lastly, I want to have a look at a couple of gameplay scenarios to basically illustrate some of the techniques that the agent learns. The first one is for the breakout game, which you're basically controlling the platform at the bottom, and then there's a projectile or a ball that you shoot up to basically get rid of the tiles on the top. The strategy that the agent learns here is to basically find an opening in the left-hand side like this and shoot the ball up there. The reason is that once it goes up here, it's going to bounce up and down and basically collect lots of points as it does so. And it's quite interesting to see what the internal model approximates the value of these states to be. So down here, we can see a graph of basically the estimated value of the states. And in the beginning, we can see that the value is not very high, but it's increasing all the time, all the way up until we make it to 4. And this is what the model itself estimates for the value function. And we can see that it estimates it very well, because when we break through the upper part here, it's going to receive lots of rewards. So the value function indicates well, what would be expected from the algorithm here. So it's quite interesting how it learns this this strategy for minimizing the amount of actions that it needs to take in order to cover the ball, but at the same time accumulate lots of reward. The second game that we have is basically Pong, where we can see a similar intuition for the state values. So we can see 3 different actions, which are the only ones you can take in this game. So you have no operation, up or down. And we can see that in the beginning here, we have a ball coming this way. The dashed lines are just illustrative, by the way, so there's no, these wouldn't be seen in the actual game, but in order to show how the trajectory is, they're included in these figures. So the agent controls the green one here. And we can see that in the starting value, basically all the actions are equal in terms of expected reward. It looks a bit off because the ball is quite close to this, so you would expect that up perhaps has the highest action value. But because the ball is still quite far away, or far enough away, let's say, they're all quite equal. And actually the down one has slightly higher action value than the up one at this stage. However, slightly, moving forward a tiny bit, we can see that here, the action value of the down and no operation drop to 0 or drop down, and the expected action for up remains high. So this is basically where the agent realizes that, okay, I need to adjust myself now, otherwise I'm going to let the ball pass and then I'm going to lose. So we can see that it starts pressing up and, well, approaches the ball. And if it presses up again, it's going to hit the ball. And again, it looks a bit like it's almost passed already, but this is accepted according to the game dynamics. So the game dynamics are such that if you move up here, you're going to hit the ball before it reaches the end. So it looks a bit delayed, and from a human perspective, you would perhaps get into position a bit quicker. But there's no, the model itself doesn't really care about that it's there well ahead of time. It just cares that, okay, I'm in the right position when the ball actually hits, and so it times it in this way. It hits the ball and then it goes back, and we can see that it passes the other player here. And right before it hits the edge, we can see that all of these basically have a very high reward. And that indicates that the model knows that it's going to win anyway. And then it doesn't really matter which action it takes. So I think the results here convey that the model really learns, gains an intuition for these games and what is important in them, even without having an internal model to basically tell them what the objective is or how anything works here. So quite remarkable that it's able to look at this visual data, devise a strategy for a number of different games, and then perform at a level that is superior to most algorithms that have been developed so far, and even comparable to most humans. So that's it for our evaluation of this paper. I think it's super interesting, and I hope you like this overview. So thanks for watching, and see you next time.